You build an autonomous coding agent. You assign it a complex task. 10 minutes later, it's stuck in an infinite error loop, hallucinating imports and confidently reporting success while your build fails. The industry reflex is predictable. Blame the language model. We assume that if we just expand the context window or wait for the next generation of model architecture, the agent will suddenly understand how to fix the problem. A 100-page survey from researchers at UIUC, Meta, and Stanford argues we are looking at the wrong layer. The ceiling on agent autonomy is not the base model's internal capability. It is the reliability of the system harness surrounding it. Production systems like Claude Code or Codex rely on the harness to manage the environment. This layer is what transforms raw text generation into a functioning coding agent. Throwing more parameters at a model yields diminishing returns if the layer translating the model's decisions into long-running stateful actions is flawed. To fix autonomous systems, we have to redefine the role of code within an agentic architecture. Traditionally, code is the final output, the text string an LLM produces at the end of a prompt. In an agentic system, code is the operative substrate, the actual medium the agent lives and operates within. It provides 3 essential properties to the system. First, it is executable, which means the model's claims can be verified by a compiler rather than just asserted in chat. Second, it is inspectable, meaning failures generate diagnostable trace logs instead of opaque apologies. Third, it is stateful, so progress persists across iterations without needing to be rebuilt entirely from the context window. These 3 properties are the non-negotiable preconditions for moving an AI from blind trust to verifiable autonomy. This diagram breaks down the architecture of any long-running agent. Engineers typically focus heavily on 2 parts: the model's internal reasoning capabilities and the system infrastructure we predefine, like API sandboxes and memory tools. But actual reliability is generated in the third component, agent-initiated artifacts. These are the temporary tests, domain-specific languages, and intermediate states that the agent creates and refines inside the loop. As those artifacts are generated, they form the harnessed interface. Code takes on 3 overlapping roles to bridge the gap between the model and the world. Code for reasoning takes invisible textual chain of thought, which models struggle with for logic and arithmetic, and translates it into an executable script that a runtime solver can explicitly score. Code for acting takes the ungrounded intent of the model and forces it into concrete, executable tool calls. And code for environment turns a black box environment into a queryable state, like a local repository or a test suite that the agent can actually navigate. This interface is the exact mechanism that converts invisible LLM guesses into grounded, measurable state changes. This cyclical flowchart illustrates the standard React loop: plan, act, observe. It relies on the model to debug until it works, and the loop only closes when the model outputs a finish token. Trusting a language model to subjectively know when a complex coding task is objectively complete is a fatal architectural flaw. We replace it with the plan, execute, verify, or PEV loop. Observation is stripped out and replaced by a rigid gateway called verify. Under PEV, the plan stage forces the agent to externalize both its intended code change and its risk assumptions upfront. Execute takes that plan and applies it strictly within a permission sandbox. The verify gate then reads deterministic sensors. Without asking the model for its opinion, the gate automatically routes the execution state down one of 4 paths. Repair and termination become mandatory consequences dictated by the verify gate, rather than a separate workflow chosen by the agent. True governed autonomy means proving a predicate held true, rather than hoping the model feels confident in its answer. Look inside that verify gate, and you find a cost-ordered ladder of deterministic sensors. Static checks, like linting and types, sit at the bottom. They run before anything executes, saving compute by catching cheap failures early. Only if the code passes do we escalate to runtime exceptions, then to unit tests, and finally to full evaluation harnesses. Natural language critiques can help interpret sensor data, but they cannot replace the deterministic check itself. Beside these sensors sits a strict permission ramp gating the execute stage. It scales from read-only browsing up to sandbox editing for running local tests. The highest tier, full access, which includes network deployment and destructive file system operations, enforces a mandatory human-in-the-loop requirement. Combining a cost-ordered sensor hierarchy with strict permission tiers removes governance from the LLM prompt, placing it securely in the system architecture. A single agent eventually hits limits. The context window exhausts, and one generalist model is inefficient at acting as a planner, synthesizer, and reviewer all at once. The industry solution is multi-agent systems, but most frameworks attempt to coordinate these agents by rebroadcasting natural language in a shared chat window. This chart reveals why chat-based coordination breaks. The top line represents SK, the ground truth of the repository. The bottom line is BK, what the agent believes the state to be. Over time, they violently diverge. Because the agent's belief is rebuilt from a text summary on every turn, this divergence is invisible to the system. The agents end up generating code for a phantom repository that no longer exists. The survey formalizes a solution across a 4-level maturity substrate. The implicit chat sits at level 1. Level 2 introduces a persistent file tree to read repository history, but level 3 introduces an execution oracle. Here, the state of the project is defined objectively by what actually compiles and passes tests. Operating at level 3 or the level 4 blackboard allows multi-agent systems to converge based on objective, test-gated metrics rather than subjective agent consensus. Scaling AI requires a formal, persistent memory space where agents interact through code execution, ensuring they never talk past each other. We can distill this entire 100-page academic survey down to a single load-bearing architectural invariant. First, an agent harness requires deterministic sensors to evaluate progress. Second, it requires a stable, queryable substrate to execute within. Third, termination of the loop must be governed by verification, not model trust. Memory modules, debate frameworks, and advanced tool use are secondary machinery. They exist solely to feed this primary invariant. An agent harness is only reliable if, and only if, all 3 of these conditions hold true simultaneously. But there is a massive vulnerability hiding inside this architecture. The entire structure fractures on one reality. A green test does not equal a complete specification. If your oracle is weak, or your test suite is poorly written, the executable substrate provides a false sense of correctness. The agent will ruthlessly optimize for the wrong signal, passing the tests while breaking the software. The agenda for agent engineering requires treating the harness as a first-class product. We have to generate evidence bundles detailing residual risk for every accepted action, and we have to convert human-in-the-loop approvals into an auditable, durable database of accountability. To achieve true autonomy, we must stop trying to optimize the model's confidence and start rigidly governing the state transition.